Lesson 4 is two-dimensional collisions, and I'm quickly just going to play a little of this PHET demonstration, P-H-E-T. And here we have two balls of different masses, and they are going to hit each other, and the conservation of momentum is still key here. You can see that when the small one hits the large one, the small one usually increases in velocity. Oh, if they ever hit one another, come on, you can do it. There we go. Bang, bang, and we can add. Can we add more here? Oh yeah, we can put more balls in there. We want. There we go. So this is a good demonstration, and you can see all the momentum vectors, the velocity vectors, and so on. Okay, I can't play too much of that because it takes up a lot of memory. Let's stop that and go to our lesson. Two-dimensional vectors. In terms of mathematics, calculations, this is the toughest thing you're probably going to do all year in Physics 30. This is the most complicated thing you're going to do mathematically. Why is it complicated? Well, it is just actually, it's not complicated. It's entirely a review of this, of vectors in Physics 20. So if you did well in vectors in Physics 20, this is going to be straightforward for you. If you didn't do well in Physics 20 vectors, then you probably need to review because this will drive you bonkers if you're not comfortable with vectors. Let's just quickly review. If I was in Physics 20 right now, we'd be doing a vector problem. We would be saying something like, you run this way, and what is that? You run 10 kilometers north, 40 degrees west, and then you run 17 kilometers east, 20 degrees north. What's your displacement, right? So this red vector here is that is my 40 degrees north, and then I've got another vector. Let's just move that. Come on, move. There we go. Let's go with the blue vector. East 20 degrees north would be something like that, and it's 17 kilometers. Right, there's my 20 degrees in there. Right, my 40 degrees in there, and this is 17, and this is 10, and you would say, what's the resultant? What's the displacement vector? In other words, tip, tip. Oh, sorry, tail, tail, tip, tip. And you have to calculate the length of the green vector and the angle, right? And how would we do this? You can do it using sine and cosine law, or you can do it with components. And we strongly recommend you use components because components will work for all problems, whereas the sine and cosine law have limitations. So how do we do that? We would say, okay, let's take the red vector. It has a horizontal component. It has a vertical component, right? And then we take the, what color am I missing here? Take the blue vector. It has a vertical component here. Let's just call that y2. And a horizontal component here. We use sine and cosine, just regular trigonometry, to find out the values of these four. We add the x's, and you can see one x is going to subtract from the other one because they're going in opposite directions. We add the y's, and then we make a new triangle. And that new triangle is essentially going to be this. There it is. It is the components of the green vector. Okay, so actually that should make a nice rectangle. So that was just a quick review of vectors. And now we're just going to apply that to momentum. And really the only added element is just this formula here. P equals mv, because now the vectors are not necessarily going to be distance or velocity vectors, they're going to be momentum vectors. So it's not terribly difficult compared to Physics 20 vectors. You can read all your notes here. Here's an example. We have two balls hitting one another. Before the collision, each of these has a momentum. After the collision, they both have momentum, and the total momentum before equals the total momentum after. That's the conservation of momentum. And it's a sketch a diagram that represents the collision between a moving pool ball that strikes a stationary pool ball. They move off at a 60-degree angle between them. So let's say we've got, so let's go with the blue. The blue is moving, it's moving, and it hits a stationary one, and they move off at an angle of 60 degrees between them. So let's say the red one will go like that, the blue one will go like that, and this angle in here is going to be 60 degrees. Okay, so there's a simple sketch of what's going on, and we have to remember that the total momentum right here equals the total momentum right here. That's the conservation of momentum. What makes this more difficult than lesson 3, one-dimensional collisions, is now that we have to deal with the 2 dimensions. Moving on, we've got, okay, you can read your notes there. Let's go on to example 3. Example 3. And this is similar to example 2. Now we're actually going to do the mathematics of it. We have a red ball moving to the right at 17.1. Let's do a little sketch here. Moving to the right, so it's all horizontal at 17.1 meters per second, strikes a stationary blue ball, BTT. If the final velocity of the red ball is 13.5 at 23 degrees above the horizontal. So in other words, the red ball is going to end up going this way. And that's 23 degrees right there above the horizontal. Determine the velocity of the blue ball. Okay, so we can probably surmise that the blue ball is going to go in this general direction. That's very general. Okay, that's just a prediction. Don't hedge your bets on that, because in the next example you'll see that you may be right and you may be wrong. Determine the final velocity of the blue ball. So we're going to find out the total momentum before, and then we're going to make sure that that equals the momentum after. In this problem, the momentum before is really easy because the blue ball is stationary, so it has no momentum. The red ball is moving, and it's moving horizontally only. So in other words, it has only a horizontal component. And how do we find out that horizontal component? Using our momentum formula. Momentum equals mass times velocity. The mass of the red ball is 1.2. The velocity of the red ball is 17.1. We multiply those together and we get 20.52 kilograms meters per second, and we have to acknowledge that that is all horizontal, or it's all to the right. So in other words, before the collision, the total horizontal component, and I'm just going to put total H equals 20.52. The total vertical component before the collision equals 0. The total horizontal 20.52. The total vertical before the collision is 0. Therefore, after the collision, you need to get these same numbers. You need to have a total horizontal component of 20.52 after the collision and a total vertical component of 0. Okay. How are we going to do that? Well, we've been given information about the red ball. We've been given the angle and its velocity. So, in other words, we can calculate, let's go green here, the momentum of the red ball after the collision, which would be 1.2 times 13.5, and that's going to equal 16.2 kilograms meters per second. And that is at an angle of 23 degrees, at an angle at 23 degrees above the horizontal. Now remember, that is the red vector here. This red vector is 16.2. What we need to do now, just like you did in Physics 20, is separate that into components. So here's what we have. I'm sorry, it's going to be a little haphazard on the board, but you can figure that out. So we know that the hypotenuse is 16.2. We know that this is 23 degrees. And we know that that vector, that momentum vector, has an x component and a y component. And with all right angle triangles, we're going to use sine and cosine to calculate the x and the y. Cosine of 23 degrees equals the adjacent. I always just do my x first, just by habit. It doesn't make a difference. Over the hypotenuse, so x over 16.2, and therefore x equals, and of course we know the answer is going to be less than 16.2 because the hypotenuse is always the longest side. And we end up getting 14.912. So this is 14.912. Let's do the same thing for the y component. The sine of 23 equals the opposite, because y is the opposite 23 degrees. Y over 16.2, cross multiply, and you end up getting y equals 6.3298. Okay, so this value here is 6.3298. Ooh, this is getting convoluted. But everything's together now, so you can kind of see how they all relate. You should be able to see, you should say that the red ball has an x component of 14.912, and the total horizontal or x component has to be 20.52. So how are we going to find out the, so let's go to the H, the horizontal component of the blue ball is simply going to be 20.52 minus the 14.912, right? Because we have the horizontal component after the collision must be the same as the horizontal component before the collision, and therefore if the red ball had 14.912 kilograms per meter per second of momentum, then the blue ball must have the remainder of that. So we subtract those two numbers, and we get 5.608 kilograms per meter per second. And then for the vertical of the blue ball, oh, that's an interesting question. What is the vertical component of the blue ball? Because we can clearly see in our diagram, let's go back up here, we can clearly see that the blue ball has a horizontal component, which we just determined to be 5.608, and it has a vertical component. And what is that vertical component? Well, we know that the total vertical components before the collision was 0. Therefore, the total vertical components after the collision must also be 0. So if the red has 6.329, what does the blue have so that they add up to 0? Well, you should probably intuitively see that it's just going to be negative 6.329, because 6.3298, plus negative 6.3298 equals 0. So the vertical component of the blue ball is going to be 0 minus 6.3298, which equals negative 6.3298, which simply means that it's going down as we expected. Okay, and perhaps I didn't do, I should have drawn my diagram a little differently. You can see that the blue ball actually is going to end up right down here because it has a much, or it has a greater vertical component and the horizontal component. That doesn't matter because we didn't know what the answer was anyway. Now that I've got these two numbers, because remember my goal here is to find the velocity of the blue ball, I can make a new triangle just like I did in Physics 20, a new triangle out of these two vectors. Let's do it over here. Horizontally, we're going to go 5.608. Vertically, we're going to go 6.3298, and since it's negative, it's going to be down, and then we're going to solve, let's get a different color, for the resultant vector right there, and the resultant angle, just like you did in Physics 20. Okay, so Pythagorean theorem to figure out R. R equals, if I'm just taking a shortcut here because I assume that this is somewhat familiar to you, and that's how you find R, right? C squared equals A squared plus B squared, therefore R equals the square root of X squared plus Y squared in this case, and that will give me, I don't have the answer, so I'm going to actually have to calculate that. Myself, oh, there it is. It's going to be 8.457 kilograms meters per second. And then I'm going to use the inverse tangent. Let's just go tangent theta equals the opposite over the adjacent, and then so we can use inverse tangent feature on your calculator. Remember, use the inverse if you're trying to find an angle. 5.068, there we go. And we get an angle of, what does it turn out to be? 48.4 degrees, so we're just going to round it off to the nearest degree, 48 degrees. Okay, now, so what we've done now is calculate the momentum, but that's not what the question was asking. The question was asking for the velocity of the blue ball. So we have to go back to our original momentum formula. We know that momentum equals mass times velocity. Therefore, velocity equals momentum over mass. The momentum we just calculated, 8.457 divided by the mass. The mass of the blue ball is 2.31. That is going to give us a final answer, a final momentum of final velocity, 3.66 meters per second, which seems pretty reasonable. And then the final answer is going to be, and just note, why I said that seems pretty reasonable. Why does that seem reasonable? It's quite a bit slower than the red ball. The red ball is going at 13.5, but remember the blue ball is almost twice as massive. So more mass, less velocity. How do we write the final answer for this question? We're going to say that it is 3.66 meters per second, and the correct way to write this, since the question said the initial red ball went 23 degrees above the horizontal, we're going to say that the blue ball is 48 degrees below the horizontal. So that is kind of a classic two-dimensional problem. It's not the hardest one. There's another, the next example number 4 is the hardest type of two-dimensional collision you're going to get, and we're going to do that in a separate video because it's already been 20 glorious minutes. Okay, hold on to your hat for the last example. And just remember, this is the most difficult thing we're going to do mathematically all year.